Hi, I'm Andrew Sornborger, and I'm going to be presenting this talk on variational fast forwarding for quantum simulation beyond the coherence time. This is joint work with Christina Sestoiu at Oxford, Zoe Holmes at Imperial. Until recently, she'll be coming to Los Alamos in another week or two. Joe Yosue at QCware, formerly of MIT. Łukasz Cincio and Patrick Coles in the theoretical group, also at Los Alamos. So I'm going to present a variational quantum simulation algorithm. This is this slide here. I compare it to the standard trotterization method. So standard method is to take a quantum simulation unitary, divide it into small time steps, and approximate each of those time steps using a trotterization, and then iterate that trotterization for a number of steps. The difficulty with this is that you rapidly run into the coherence time of the quantum computer, and so you're severely limited in terms of the amount of time that you can simulate. Our approach, which we call variational fast forwarding, or VFF, takes a simulation unitary, we then trotterize it, but then we compile it into a particular form, which looks like this. It's a unitary W with a diagonal unitary and then Hermitian transpose of the original this original circuit unitary. And so what you can see here is that with this form, we've diagonalized the original trotterized quantum simulation Hamiltonian. And what that means is that we can exponentiate this unitary by hand, simply by modifying the parameters, the parameter delta t inside the diagonal, and multiply it by some n, which will then give us a total simulation time t, which can be longer than the coherence time because this entire circuit, which is used for the simulation, lies within the coherence time. Our algorithm looks like this. We have an input Hamiltonian. We form a unitary and trotterize it. The trotterized unitary is what we're trying to find. And the way the compilation works is we take our parametrized diagonalization and try and match it to the trotterized unitary. We do that using gradient descent, and that's done using what we call a local Hilbert-Schmidt test quantum circuit. This circuit can be used to evaluate the cost as well as the gradients. Once our cost is down to some threshold, we then have an approximate diagonalized trotterized simulation unitary, and we use that in the way that I said before. By hand, we simply multiply the parameters in the diagonal by whatever number we want in order to get the simulation time that we want, and we have a fast-forwarded quantum simulation that only uses the same size or same depth circuit that was used in order to do the original optimization. So the circuit that I'm using here is a local cost function circuit, and I want to point out that there's a difference in terms of barren plateaus between local and global cost functions. This is the cost function that you might expect to use for the kind of matching that we're doing between unitaries. It gives you, if you evaluate the expectation value of the zero output state, you get this. The problem is this factor here is 1 over d squared, where d is 2 to the n, and n is the number of qubits. So as your qubits grows, this rapidly gets very small. So unless u and v are very close to each other, this is essentially a flat landscape and has a barren plateau. Unless you're exponentially already close to u, you'll never be able to find it because the gradient is effectively going to be 0. So we use a local Hilbert-Schmidt test. It can be proven that this circuit using this cost function, which makes multiple uses of this circuit, is faithful to this cost function. In other words, where this cost function has a minimum where this one does. But notice that this factor is 1 over n, and so we're just polynomially the landscape only decreases polynomially versus this exponential decrease. And so this avoids, to a large extent, barren plateaus. So the VFF algorithm does this optimization, performs this optimization, and still at the end of the optimization, you have a bunch of errors. So the total error, which would be the original exact quantum simulation unitary minus the diagonalization, consists of two kinds of errors. One is the trotterization error. This is already, this error exists when we input our trotterized simulation unitary to the optimization circuit or loop. And but then we also have the machine learning error, which is when we set a threshold for our cost function, it's always going to be finite. We can't actually bring that exactly to zero. And so what happens is you can prove that the fast forwarding error, the error of the simulation after you exponentiate it for time capital T, is always less than or equal to the number of time steps it took for that exponentiation times the Trotter, Suzuki, and the machine learning error, the sum of them. And you can translate this roughly into the fact that the cost function will always be less than about n squared times the cost function at the end of the optimization loop. So you can, in an example, this is a single qubit unitary that we diagonalize using VFF. This is simulation. This is in simulation on a classical computer. But you can see here, so what we've done is we've optimized within about 30 steps, we can get roughly down to 10 to the minus 6 optimization error. And the related simulation error, which in cyan is this is the infinity norm or the cost function. We've squared the infinity norm, so these are comparable. We plot both of those as measures of the error of the simulation. And you can see that they always lie below this line, which is effectively the initial value of the cost times n, where n is the number of time steps that you take in your simulation. We've used this method on a number of different systems. In this example, I want to show you that show you kind of a method that we've come up with in order to rapidly diagonalize and find new diagonalizations for a given model with a bunch of different parameters. So what we did here was we turned off all of the couplings in the Heisenberg model. There was only a magnetic field. And we diagonalized that Hamiltonian. So that's essentially equivalent to just diagonalizing a bunch of independent spins. But then we gradually turned on the couplings. We turned on JZ, the ZZ coupling. And you can see that we very rapidly could diagonalize nearby models by starting off with initial conditions that were kind of close by. So there's a little bit of a perturbative type approach. We then turned on the X and the Y couplings. Then it took a little bit longer to find a diagonalization, but it found it. And then we just gradually turned on these numbers from 0 to about a factor of 8 or so. And then in this part of the optimization, JX and JY, we set to be the same. So this was an XY model. But then we allowed the Y value to change, and we found that we also could very rapidly find diagonalized models. These are the simulation errors for all of the models here, all of these cyan X's. And you can see that we got a range of fast forwardings between about 70 or 100. This is an example where this was done on the Rigetti chip. And the thing to notice here is that the Trotter error, so this is iterated Trotter, starts off relatively high in terms of entanglement fidelity, but then rapidly goes down. So 0.8, 0.6, 0.3, 0.5. So it rapidly goes down below about, to 0.5 or below. For VFF, though, you can see that the error stays high much longer. Another thing that we can do with this method is to use classical signal processing methods in the way that Rolando Soma has introduced recently in order to estimate eigenvalues. Here, these are eigenvalues for a 2-qubit Hubbard model, 2-site Hubbard model, and these match very nicely those that you would find in a classical diagonalization. So in summary, using quantum-assisted quantum compilation, we've shown that with an appropriate ansatz, one can diagonalize a trotterization of a quantum simulation unitary nicely. With the resulting diagonalization, one can exponentiate the diagonalized unitary by hand to simulate beyond the coherence time of a quantum computer. We've derived rigorous bounds on the simulation time dependent on the optimization error, and we've shown that this method works in simulation and on few qubit unitaries on extant QCs. Thanks very much. Sorry I'm not here for questions. Feel free to email me at Los Alamos.